Welcome to Mrs. Mahoney's podcast 4.4. Today we're going to start talking about nuclear chemistry. And if you've noticed, I've been putting the page numbers and the chapter numbers so you can always go and reference the book. And look at this, we're way back in chapter 25. I'll be honest, nuclear chemistry is a topic that we really never know where to put it. I've put it at the beginning of the chapter, I've put it at the year, I've put it at the end of the year. We put it in the middle of the year. It's just different than anything else we're going to talk about the rest of the year. So it's kind of like we're saying, okay, there's these reactions and we're going to balance them. The good thing is they're easy, but then we're never really going to do anything like it again. You'll revisit it in physics, but not in chemistry. So let's look at what the difference is. So we have chemical reactions. What is a chemical reaction? Well, atoms will form bonds when you make compounds. So this is under the slide that says chemical reactions. If a chemical reaction happens as a property of both the elements, hydrogen and oxygen will make water. Well, that's a chemical property of hydrogen and oxygen. A key thing, when you have a chemical reaction, when we start balancing, we're going to have sodium on both sides of the arrow. I had sodium, maybe neutral sodium, and sodium as an ion, but it's still sodium. And the fourth thing, when we have interactions, we're talking about a change between the valence electrons when we're talking about chemical reactions, the outer shell electrons. Let's compare that to the nuclear reaction. If I have a nuclear, it's really a property of just that single atom, and it's a reaction that's happening just within that single atom and not with it reacting with something else. You get spontaneous changes. If it's not stable, it's going to do something, change it to make it stable. Here's some big ones that their reasons are different. We have changes in the nucleus. We're going to be changing and/or neutrons. So if we're going to be changing protons, if we're going to change protons and neutrons, we're going to be changing elements. That's a huge difference, and we're only going to see it for about this next week, and then we won't be doing it again. And again, because we can change protons, we could be changing an element into a new element. We're going to be changing the number of protons, which I said never ever change. Then this is a little side note. Unless we're doing nuclear chemistry, that's the only time we're going to change it. So why does this happen? It's all about stability. Everything, even chemical reactions, losing valence electrons, gaining valence electrons is stability. Same thing with nuclear. It's all about how many protons and neutrons are in the nucleus. So what affects it then is just that ratio of neutrons to protons. Because the more mass that you start adding in there, let's look within the periodic table. If you just kind of take the periodic table and we look through it, pretty much up to about element 20, you have about a 1-to-1 ratio. If you look at the mass, it's just about double what the atomic number is. So you have equal numbers of protons to neutrons. But what happens is, as you start putting in more positive protons, they are trying to repel each other. So neutrons actually act like a glue holding it together. So as you get more protons, you're going to have to get neutrons. And up at your higher elements, you have that ratio that gets up to 1.5 to 1. So meaning you have 1.5 neutrons for every 1 proton. And again, it's increasing that nuclear force, and that strong nuclear force is just one of the fundamental forces that holds the nucleus together. So okay, if we look at this graph, you have it in your table. Let's just kind of look what it means. You have it in your packet. What this is saying, this is the high range, so that 1.5 neutrons to 1 proton. This is the lower range of a 1-to-1. If an element falls within this range, we say it's stable and it's not going to undergo nuclear decay. So let's look at when it starts to fall outside of that, and that's clear up here at the top, and that's where we're starting to see that it's getting out of that ratio. So something's going to have to change in the nucleus. The reason it happens is to get this ratio back into the band of stability so we can change protons into neutrons, and we can have all different kinds of reactions, decay, to get that to happen. Well, the binding energy is really when we're talking about the energy, it's released or we can say it's the energy needed to split an atom. So when we start talking about splitting atoms, it releases a tremendous amount of energy. And when we look at the nuclear reactions, fusion and fission in a couple days, this is the energy we're going to be tapping into, and it takes a lot of energy to do it. That's why to break an atom, to smash an atom, you have to be going extremely fast, get those particles going extremely fast. So the higher this energy is, the more stable the nucleus, or how it's worded in your packet, look at the inverse. So the lower the binding energy, then those are the less stable atoms. So if we look at this chart, it's just again kind of another way of looking at it. Where are my stable atoms? Well, if you look at these are like your transition metals. These are my very stable ones. You don't see very many nuclear reactions going on within there. If I start getting too low, we're going to get some fusion. I start getting higher, that's when I'm going to get some fission going on, which we'll be talking about these specifically in a couple days. So where does this happen? Okay, make a little note, and I know that when we did that activity looking at the periodic table, I'd said this, but remember, elements after bismuth, that's where my radioactive, and those are my unstable elements. So we're really going to be looking, so when you're searching for those elements, I would look down there on that 5F. We're looking at the higher elements when you're trying to find it. Okay, so a quick review. Hopefully this is review, because this is also remember this will be potentially on that test in the CA. When we're looking at this, remember the mass number is the number on top. Okay, the atomic number is the bottom number. Your mass number was the total of protons and neutrons, and your atomic number is just the total protons. So when we have to balance these reactions, when we start writing them and balancing, these are the numbers that need to be the same. They need to be balanced. So you have to do 2 times. We're going to do some adding and subtracting. So the numbers on top, your mass numbers on both sides have to be equal, and the mass numbers on the bottom of all the things added together have to be the same. And when I start balancing, that'll start making more sense. So what happens if it's not stable? It's going to have some kind of decay, and we call it a radioactive decay. And what does that mean? That it's going to spit out some particles, and some energy is released by the nucleus of an atom. So we have 4 different types of decay that you're going to be seeing. And again, we're borrowing from the Greeks. So this is our first type of decay. It's called an alpha decay. This is the alpha symbol. An alpha consists of 2 protons and 2 neutrons. So if I have 2 protons in, these are both positive, it's a positive 2 charge. And what's its mass? So this is 2, this is 2. Its mass is 4 AMUs. This alpha, it's the biggest, it's the heaviest, it does the least damage. This is all around you. Your skin, though, protects you from alpha decay. So if we look at this, it really is just a helium, but this is where it's different. It's just a helium nucleus. Or the nuclei, because we do talk about more than one. This is the helium nucleus. We're not worried about electrons in there. It's only focusing 2 protons, 2 neutrons. So this is happening when it's just too heavy. We need to reduce the total numbers. Then this is going to spit out an alpha particle. So what does this look like? Let's write down an example. So if I have polonium-210, so I would write that polonium, remember mass number goes on top, find the atomic number, 84, and this is what it would look like. It's going to actually lose an alpha particle. So then what's left behind, I know, is going to be 4 lighter. So what's left behind is a 2O6, and it's 2 protons less, 82. So what element did it just, so from the periodic table, we can see it just turned into lead 2O6. And it's done that again to decrease this ratio to get it back into that band of stability. So you're going to have to be able to, by the end of a couple days, recognize that this is an alpha decay. I know it's an alpha decay because right here is an alpha particle it's losing. So yes, you need to know that 4,2-HE is alpha. You need to know that, flat out. You need to know that. And then you can see that it's making something new because it lost this alpha particle. So our first type is alpha decay. Okay, second type of reaction you're going to see is called a beta decay, which is B in the Greek. Alpha is A, beta is B. So this beta particle is really an electron. So if it's an electron, what's its charge? -1. What's the mass of an electron? We say 0. Okay, when this happens, really what happens is you get a neutron. This neutron transfers, changes into a proton and an electron. And let's look at this neutron. If I have a neutron, it has a mass of 1 and no charge. That's my symbol for a neutron. So let's look at how that happens. If it's a proton, it has a mass of 1 and a charge of 1. That would be a proton. But an electron is a 0, -1e. So 1 plus 1 is 1, plus 1, -1, neutron. So that is really what this neutron is composed of. Now we're getting into quarks and all those different things that is not what we're getting into at this level. Just know what happens, that this is what can happen. So what it does then, it's going to spit out the electron. Okay, it doesn't literally spit it out, but it's emitting it, and remember that's what that emitted means, it's giving it off. That proton stays behind. So what it's just done is change that ratio by changing that neutron into a proton. Okay, this is our symbol again because it has 0 mass, -1 charge. So whenever you see this, you know that that is a beta. Okay, now sometimes you'll see it's just as a beta decay, and you need to know these mean the same thing. So you need to know alpha is 4.2He. You need to know beta is 0, -1e. You need to know them. So let's look at an example of this one. Curium. So if I find curium, again, we're way down on the bottom in our 5Fs. So I have curium 248, 96, and it's saying that it is going to lose a beta. E. Now sometimes you'll see it written like this. Same thing. These are equal. They mean the same thing. Some books, some tests might put the E. Some might put the beta symbol. They mean the same thing. Then what happened? Well, it didn't change the mass number, but look at what it did. It changed this into a proton, so you actually saw an increase in the atomic number. So it was turned into berkelium. And again, this is the math. Watch the negative sign on the math. And the math has to add up. So 248 plus 0 is 248. 97 plus a -1 equals 96. So the math all ends up. You still have to be balanced. We can't just randomly be losing things. They still have to be balanced. Okay, the next kind of sample we're going to get is a little bit different. And here's your key word. Because you're not really spitting it out anymore. We're not emitting. We're capturing. So what happens is an electron on the lower energy level falls into the nucleus. And again, remember, this doesn't happen in all atoms. This is when things are not stable, and so they're trying to become stable. So if it falls into the nucleus, it's going to actually combine with a proton to make a neutron. But again, it's just an electron, so it's a -1 charge, and it has that 0 mass. So this is the only type of decay we're going to look where we're not spitting out the particles. They're not going to be written, hence this means not on the left side of arrow like the other ones were on the left side of the arrow. It's being captured, so it's going to be a reactant, means you're going to show it up on the right side of the arrow. But look at the sign is the same. 0, -1, electron. Now, traditionally you don't see the beta in here. You see it as an electron. So what would that look like? Well, if I have radon, 222, that's the mass number, and it's 86. what happens? It captures, it adds an electron. So now this electron is being added to this nucleus. So it's going to make something new. And again, the math has to add up. So 86 plus a -1 means it's turning into acetine as it goes through that. Okay, our fourth kind of radiation is actually the easiest mathematically because you don't have to do any math. Okay, this is a gamma. To write that gamma, if you look, it's just kind of like a Y with the loop on it. That's our gamma. Well, gammas have 0 mass and 0 charge. So technically we could write 0, 0. 0 mass, 0 charge. Gamma rays are very, very high energy light. These are your dangerous ones. Beta are a little bit more dangerous than gamma. Betas are a little bit more dangerous than alpha. Gammas are a lot more dangerous. Gamma rays are when we start thinking about nuclear and we think about radiation and dangerous radiation and it's going to burn you, it's going to fry you. We're talking about gamma rays. So they're very dangerous, they're very energetic, but the thing is we typically don't show this in a reaction because it doesn't have a mass or a charge. There's nothing to balance. So a lot of times if we see that, we just don't bother writing it, or if we see it plus gamma, we don't worry about balancing and we don't freak out because there's nothing to balance in it. It's one of those just kind of extra information of what we see. So tomorrow we're going to look at some gizmo. And again, this is the gamma. It's the most dangerous. But tomorrow we're going to do some gizmos and practice on this. And then when we start tomorrow's podcast, we're going to start by just comparing all these particles and then just do more practicing of writing the equations. And I do promise this is one of the easier sections, and we usually do like balancing nuclear equations because I'll be honest, it's easier than our other reactions. See you tomorrow.